Hello. So welcome to the uh, assignments of week 6, the sample questions for week 6. So let us start. My voice audible? I think my voice is audible. So first question. The first question is about you have to comment whether the statement I will write that is true or false. So this says a PLL system can only be used just for phase tracking but not for frequency tracking. Whether this is true or false. Yes. This is false because we know if we use the PLL circuit, that can also be used for tracking the frequency and also phase. Depends on what sort of modulation we are taking. If it is FM, then we can use the frequency modulation. बोल मैं So the right option is false. Basically, the PLL can be used for frequency and phase, both tracking of both frequency and phase. Let's move to the second question. The second question, it is given a PLL with some particular specifications. First specification is the input signal that is we are providing into the PLL is x of t is equal to sine of omega c t plus theta it. Also we have given what is the output yt, that is cos of omega ct plus some theta output of t. So basically xt is the input, yt is the output, and the constant of VCO is c is equal to 2. Now the question says that assume the transfer function of the loop filter that is used in the PLL, that is h of s is equal to 1. The phase error that is theta e of t, e is the subscript for error, is the initial minus the input minus output, and this is very small. So the phase error is very small, that is the only key part here, and the input is given, output is given, and VCO frequency is also in omega c. So if the input phase theta I of t is a function of the frequency plus some phase phi 0, then what is the steady state error? That can be represented by this t tends to infinite of the error, that is the steady state error. That t tends to infinite, what will be the error? The small error. Okay, let us solve the question. So basically the information that has been provided here, that the phase error is very small. For this sort of thing we should use the small phase error analysis formula. Now, what is the small phase error analysis formula? Like theta e of t in terms of time, we can write it as limit. We have to find out, that is theta e of t, and if we convert it into the Laplace domain, that is theta e of s, that is equivalent to s of s plus a k h of s into omega 0 minus omega c by a square plus phi 0 by s. So what is a here? A is equal to 1 because a is the amplitude of this xt and it is 1 here. And also c is 2 given in the previous statement. So we can write k, the constant k, equal to half of cb, where b is the amplitude of output signal. Like this amplitude is the coefficient of the cos. So basically this is the cos waveform, and we can think this has amplitude b, this has amplitude a. So basically from here we can write that b is equal to also 1. So k is equal to half into two into 1, that is 1. So you can write limit of t tends to infinite theta e of t, that is the steady state error, that is limit of s tends to 0 and s of theta e of s. So it's easier to write limit of s tends to 0 and just put the values of a, b, a, k, h of s equal to 1, that is given in the question. So if I put all these equations here, this equation just simplifies to s of s plus 1 into phi 0, and it is equal to 0. So this is the answer. Okay, let's move to the next question. So the next question says, this input signal here is sine of omega c 1 plus del of t. Then what will be the steady state error? All the remaining things are same. So basically just take this equation once again. This is the key equation for small scale error analysis, but here the only change is we have to that is omega 0 is equal to omega c into 1 plus delta. So if we put this thing in this equation, it will be like limit of t tends to infinite, theta e of t is equal to limit of s tends to 0, s of theta e of s zero minus omega c by s plus 1, and this is actually del omega c. So it states that if the input signal is sort of sine of omega c into 1 plus del of t, small error 1 of del, there is a small error del, then this will be reflected in the PLL detection. So the error in the PLL circuit, that will be a linear function of this frequency. Del. Now let us move to the question number 4. Question number 4 says, the input signal is like previously, it was sine of omega c t plus theta I of t, and then for the question described in question number 2, we have given that omega 0 of t, value of omega 0 of t is 2 into 10 to the power 6 radian per second, and also the free running frequency of the VCO is omega c is 10 to the power 6 rad per second. Also we have given what is the VCO constant, that is c, value of c. So basically value of c here it was 2, but here it has been changed to c is equal to 4 into 10 to the power 6. and the point is theta e is no longer small and negligible. So the initial phase error initially the phase error that is also given is pi by 18. Then the question is, what is the equilibrium value of the phase error? So the difference here is, in the previous question we have thought of small scale phase error, but in this question it is no longer small and negligible. So for this type of question we have to do large error analysis. Of the PLL system. So if we want to do some large scale error analysis of the PLL, the rate of change of the error with respect to time can be written as in this format. So we know previously also in the question A is equal to 1, B was also 1. Now only C has been changed. C is 4 into 10 to the power 6 here. So K we can find half CB, the same formula. So this is 2 into 10 to the power 6. And what else are given? This omega 0 value. What is the omega 0 value? 2 into 10 to the power 6. And omega C value 10 to the power 6. So omega 0 minus omega C is equal to 10 to the power 6. So for equilibrium this will be 0. Basically the error will not change with respect to time at equilibrium. So at equilibrium the equation will be zero equal to 10 to the power 6 minus 2 into 10 to the power 6 sine of theta e. From this equation. And then we can write theta of E is equal to 2 pi n plus pi by 6. This is one of the solutions of this equation. If we want to find theta e, what is the value of theta e? Another solution is 2n plus 1 pi minus pi by 6. Now at theta e, equal to pi by 18, d theta dt is 10 to the power 6 minus 2 into 10 to the power 6 sine of pi by 18, and this is greater than 0. So therefore we can comment that the equilibrium point should be at least theta e such that theta is greater than pi by 18. And also d theta e by dt to 0. So what will be the equilibrium point is pi by 6. Why you have taken this pi by 18? I think it is clear to everybody. I am not repeating this thing because the initial phase error it was pi by 18. So that's the reason should be at least greater than pi by 18. That is the answer, that pi by 6. Now let us move to the next question. The next question says that everything is same as question number 4, only except the fact that the value of C is here 10 to the power 6. Then the question is the same question, what is the equilibrium value of the phase error? So the same equation will be followed up here also. And it says in this time only K value only changes. It is half of CB, that is 0.5 into 10 to the power 6. Therefore, the rate of change of the error with respect to time can also be written as 10 to the power 6 minus 0.5 into 10 to the power 6 sine theta e. And this value is obviously greater than only this value. If I just omit the factor 10 to the power 6, because this value can maximally take the value 1. So it is, and obviously it will be always greater than 0. Because the function value will be between -1 to 1. So therefore there is no time, so we cannot find any value of theta e for which the rate of change of error can be 0. So for if the VCO constant becomes like 10 to the power 6 instead of the previous equation that was 4 into 10 to the power 6, then we can't reach any equilibrium. Okay. Now let us move to the question number 6. Question number 6 says we are going back to the question number 2, but just modifying the input signal once again. That is now omega c into 1 plus del of t. So again, this is for the small scale phase error analysis, not for large scale phase error analysis. And obviously it is 1 here. Another thing that has been changed in this question, that is the transfer function of the loop filter is not 1 here, instead it is s, you can write that h of s is s plus 200 by s. So basically we have to find out the steady state error once again. So just repeating the question once again for the clarity, that we have input signal x of t, that is sine of omega ct plus this sort of input sequence, and output is also cos omega ct plus theta 0 t, and other things are remains unchanged at the question number 2. Only the transfer function of the loop filter is changing in the PLL, and the loop filter is not, the transfer function is not 1 in this case, instead it is a function of s into s plus 200 by s, that is a transfer function in this question. That is the only change except the input frequency. So we have to find out what is the steady state error once again. Okay. So again we have to use the previous equation for the small scale error analysis. So we know for small scale error analysis that limit of theta e of t at time t tends to infinite can be represented as limit of s tends to 0 s of theta e of s. So we know what happens if we are calculating for small scale error analysis in the PLL. It will become like following the previous question. It is a squared by s ak, and here it was h. So what is the value of h here? It is not 1 right now, it is this function into omega 0 minus omega c by square. So this is s tends to 0, s into del omega c. Why del omega c? Because omega 0 minus omega c is equal to del omega c from this input relationship. By a square plus ak s plus 200, and that is equal to 0. This is the answer. Okay, now let us move to the question number 7. So question number 7 is some sort of MCQ question. It says, which of the following functional module is not required in the Costas loop? For a DSP-SC signal. A low pass filter, a band pass filter, a PLL, and a phase lifter.
Sir, can I know what is option B, phase?
Phase lifter.
Okay, thank you.
So basically Costas loop has all these following components. A low pass filter, it also requires a PLL, and pi by 2 phase shifter. That we can also say this phase lifter is phase shifter. That changes the phase by pi by 2 factor. So basically these three components is required here. So low pass filter is option gone, PLL gone. So only band pass filter, this is not required for a Costas loop or a DSPC signal. Okay, let's move to the next question. This question you have to comment whether this is true or false. So statement I am writing down. So basically a non-ideal amplitude or phase response of a linear distortionless channel does not create any inter-channel interference. So you have to comment whether this is true or this is false. So the catch here is it says it only can distort the amplitude or phase response. But whatever the distortion is, it is a linear distortion. This basically it is a linear channel, not there is no non-linearity. For such reason, it is impossible to create a inter-channel interference. The only thing that can happen here is intra-channels sort of thing. So the correct option is true. Let us go to the question number 9. So question number 9 is also a true or false statement. False option. I am writing the statement. You have to comment whether it is true or false. So it says in a FDMA system, a non-linear channel causes inter-channel interference and in-band distortion. Whether it is true or false. So again, it is written here that in this case the channel is non-linear. So basically this nonlinearity, you can think it is getting multiplied by some another frequency f. Whatever the input frequency, that is just shifted by some another frequency del f. So one example is, if you have a signal cos of omega ct, it get transferred into cos of omega c plus del omega not t. So this is some nonlinearity. This is the nonlinear nature here. So if this kind of thing happens in a FDMA system, so obviously that will be a interchannel interference will happen here, and also in-band distortion can also happen, because suppose the amplitude or something else or some phase has been added here, del theta t. So all this in-band distortion can also happen. So the correct option is true. Okay, so let's move to the last question of today. So last question of today is a numerical question, and let me define the question first. So what are the inputs of the question are given. I'm just writing it first, then I will ask the question. So basically let me start it. It says, consider there is a nonlinear channel and the output of this nonlinear channel y of t is a function of the input xt with in this form, like yt is equal to x squared t, and xt is the input. So statement is, let x of t, the input signal, is a DSBSC. DSBSC, tone modulated signal. And with the message bandwidth omega m, and also the center frequency omega c, such that obviously the carrier frequency will always be greater than omega c greater than omega m. That is the only condition. So that is not such a vital condition, we all know that. So if the output of the channel So what is the output? This yt is demodulated by passing it through a multiplier with frequency omega c. So it is demodulated by passing it through a multiplier that has a frequency omega c, and then it just pass through a low pass filter. So then what is the final output? So again, just clarifying the question once again. So we have a input xt, and xt is a DSP-SC tone modulated signal with message bandwidth omega m and omega c. So it is going through a channel, and the output of the channel is yt is equal to x square of t. So in the receiver we are demodulating it by multiplying it through multiplying with the frequency omega c, and then we are passing it through a low pass filter. So if we do all these things, what will be the output of final output after the low pass filter? That is the question here. Okay, so let's solve this question. So what was the statement? xt is a DSP-SC tone modulated. So what is xt? xt is the carrier frequency into the message. So if xt is this, what will be the yt? Yt is cos square omega ct into cos square omega m t. So if it says this yt is getting multiplied by a frequency omega c, this part by a multiplier, demodulated. So what will be the output of the multiplier? It will be z of t is yt getting multiplied a cos omega ct. So this is equal to cos cube omega ct into cos square omega m t. This is equal to 1 by 4 cos 3 omega ct plus 3 cos omega ct into, basically we are simplifying this term. This is the first cos formula. The second is 1 plus 2 cos omega m t. So if we simplify it more, it will become 1 by 8 3 cos omega ct plus cos 3 omega ct 3 by 2 cos of omega c plus 2 omega m t plus 3 by 2 and the term will be, just take it common, plus cos of omega c minus 2 omega m. Just let me write in the fresh page, that will be better. Basically if I simplify this, it will become, so yes, it will become 1 by 8 3 cos omega ct plus cos 3 omega ct plus 3 by 2 cos of omega c plus 2 omega m t plus 3 by 2 cos of omega c minus 2 omega m t plus half 3 omega c plus 2 omega m t plus half 3 omega c minus 2 omega m t. So every term has a component omega c, omega c, omega c, omega c. There is also omega c term and this is omega c term. So basically if it goes through a LPF filter, this output ZT goes through a LPF filter, none of these components will go through the LPF filter. So what will be the output? Output will be 0 always. So the answer is 0. Okay, fine. So anybody has any doubt about today's session? Any of the questions? Okay. Then we will meet in the next Sunday.